Uh, this cast is going to be dealing with conventional current flow versus um, electron current flow. You'll have to excuse my handwriting. It's bad enough in normal conditions, but I'm just getting used to using this piece of software that lets me write on the screen with a stylus and talk, just like I was at the whiteboard. But we'll get there. I hope you're having a good, safe time in your quarantine at home. And this is hopefully going to be the next best thing to being live in the classroom. This topic really is something I would teach at the beginning of TY 221, which I haven't taught here yet, but it applies both to some things in motor controls and in solid state. So this is a good time to throw this in for both classes. I think I have mentioned it before, at least in motor controls. I don't know that we've had a need for it yet in the solid states. We've been doing AC stuff. And this is really a DC topic because AC current flows in both directions. It alternates. That's why we call it alternating current. DC really flows in just one direction at a time. Let me open a new page here. And we can think of that current in two ways. First of all, there's the electron flow version. That's supposed to be a W. All right, we have a DC supply, and we'll have a resistor over here. DC voltage, resistance, and let's just say we've got 20 volts and 10 ohms. Now, without even drawing the current, we know that I is V over R. In this case, that's 20 over 10 will be 2 amps. Now, that applies no matter which direction I assume the current flows. In electron flow, we say that we have a negatively charged particle comes out of the battery, the negative side of the battery, into the negative side of the resistor voltage, and back to the positive side of the battery. Now, I know the positive side from the negative side of the battery because of the narrow line here is the negative side here. Oh, I didn't mean to do that. Sorry, I'm still getting used to the software. Bear with me. Anyway, the narrow line's the negative side, and the wide line's the positive side. Now, if we look at conventional flow, and let's take the same circuit. Hang on, bear with me here. we'll take this. I'm not going to put all the numbers on here, but assuming we get the same V and the same R, we still have the same result for current, except with conventional flow. And this happens because back when electricity was first discovered, they used something that was moving around the circuit. They just wasn't sure what. So they assumed there was a positively charged particle, comes out of the positive side of the battery, goes through the circuit and returns back to the negative side. Now, in both cases, I'm calling that I, and I still end up with the same polarity of the resistor. That's a voltage polarity. Of course, resistors themselves don't have a polarity. And the same math still works. What we have here is a condition where two wrongs do make a right. You've heard two wrongs don't make a right, and that's true most of the time. But you've also probably heard enemy of my enemy is my friend. So that's another case where two negatives make a positive, just like in mathematics. Negative of -1 is, guess what? A +1. And that's what's happening here. We're assuming the wrong polarity of the particle, but we're also assuming the wrong direction of the current. And it's a mathematical thing. Two negatives make a plus, so it really doesn't matter which one of these conventions that you use, the conventional flow or the electron flow. I do teach both. That's what we're doing today. But most of the time, I'm going to use conventional flow for a couple of different reasons. The main reason it's still around is because people just tend to think more in terms of positive things than they do in terms of negative things. And second to that, let me start a new page. The schematic symbols that we use in solid state and some things that we use in motor control work better with the positive conventional current flow than with the electron flow. A diode, which we're about to get into, well, that's going to be my next podcast. The diode, and I didn't draw a very good one, I got diodes, is one place where it shows up. In the schematic symbols, what we use for solid state, several of them have arrowheads built into them. This is a schematic symbol for a diode. Now, what a diode is, it's basically a valve for electrical current flow that passes current in one direction and blocks current in the reverse direction. If we talk about this in terms of airflow or hydraulic fluid flow, there's a device called a check valve that does the same thing. It passes current flow in one direction, blocks current flow in the reverse direction. Now, if I'm using conventional current flow with my diode, the conventional current flow agrees with the arrowhead in the diode. It passes current in the direction the diode arrow is pointing and blocks current in the reverse direction. So the schematic symbol agrees with the current flow. Now, if we're talking about electron flow, the diode passes current in the direction opposite the diode's arrow and blocks current in the direction the diode arrow is pointing. So to me, that's very backwards. I tend to try to make, well, it's obviously the diode schematic symbol was designed using conventional current flow as a model. Now, we have already been talking about on some videos I've asked you to watch about what happens inside the diode and why the diode works like it does. P-N junction is basically a diode. And when we do that, we do need to talk about electron current flow to understand it. So I will use electron current flow when I'm talking about what's going on inside of a component like this. But all other times I tend to use the conventional current flow model. I want you just to understand both of them. And a transistor works kind of the same way. And there are lots of different kinds of diodes and lots of different kinds of transistors. This is the most basic diode schematic symbol. And this is the most basic transistor schematic symbol. It's a 3-terminal device. And if you notice, there's an arrowhead built in here too, and it's basically a diode. If you leave this top connection, that's called the collector. This is the base, and this is the emitter. If you leave the collector open and just use the base and the emitter, they behave exactly like a diode. In fact, it is a diode. It's got some extra stuff going on that you can connect if you want to. But there's nothing wrong with using the base emitter junction of a transistor as a diode. Just leave the collector open. But it's the same thing. Conventional current flows in the same direction of the arrow is pointing. Electron flow goes just the opposite. So I always use conventional current flow, and I'm going to use a solid line like I did here to represent the conventional flow. If we need to talk about electron flow, I'll use a dashed line for electron flow, just like we did here. So I'm working on some other material to have out to you either today or tomorrow, so be looking for that, but this is something to keep you busy for a little while till I get that out. And you will need this ideas when we start talking about diodes. Oh, and when in motor controls, we're going to be talking about solenoids. And one of the first slides in the PowerPoint is talking about the left-hand rule. And it's, I'm not going to try to draw the picture here because we're going to look at it in the next presentation anyway. But and it's more complicated than just a schematic symbol. But the left-hand rule says if I take a solenoid, which is a coil, and run a current through it, if I wrap my 4 fingers around the coil of the 4 fingers of my left hand around the coil in the direction of current flow. Now they don't specify, but what they're using is electron flow. Use your left hand for electron flow. Use your right hand for conventional current flow. If I wrap the fingers of either hand, from depending on which current flow I'm using, if I wrap my fingers with the left hand in the direction of electron flow, my thumb's going to point at the north pole of the magnetism that's produced. If I'm talking about conventional current flow, if I wrap my right hand finger around the coil in the direction of conventional current flow, then my right thumb will point in the direction of the north pole of the magnetism that's produced. So anyway, that's why this is important. I want you to know it both ways. Even though each textbook may only present it in one way, I want you to understand the difference. So anyway, that's all for this cast. I hope you're all staying safe, and you can catch me on email if you need to. I check my email at least once a day, usually more than that. Weekends might only be once a day, but weekdays usually 2 or 3 or 4 times a day at least. So I hope you're having a good isolation period. And again, if you've got questions, just shoot me an email, and I'll try to get it answered within 24 to 48 hours at the longest. Y'all have a good day.